Greetings, my ladies and gentlemen. Good morning, good evening, good afternoon, wherever you are wherever you are geographically. Welcome back to my sessions. My name is Dr. Mohammed Nizami. I'm coming to you from Jerash, Jordan. You see in the background. Um, I have been doing tons of videos on the techniques of RF and microwave circuits and systems design. I have my own consulting organization that specializes in dealing with offering design consultancy to clients that don't have RF in-house and RF designer, or they may have more work that they can handle for their own team. Basically, you could contact me via the email that is on here, okay, which I will show you in a minute. Okay, this email, you could contact me via this phone number or via my email, which unfortunately I didn't write it here, but Mohammed underscore Nizami at msn.com. Basically, I work with clients from concept to specifications to system architecting, system modeling and verification to RF PCB board layout and bill of material and BCBA files for fabrication. I design everything from DC to 35 gigahertz. Okay, ladies and gentlemen, before we start today's lecture, I would like to bring to your attention um, my YouTube channel. This is where this presentation is posted. And so are close to, let's see, 112 videos now are on there on various concepts of design and modeling of RF and microwave um, devices and systems. So I urge you to visit the site and benefit from it. Please subscribe and share it with your colleagues so you get the benefits of this. And the topics vary from antenna design all the way to via transition design. So in between is actually RF circuits for transceivers, transmitters, and design and receivers. To, for instance, here magnetic isolators and circulators, the actual design. 6G, 5G type transceivers, um, crossovers, transitions, a lot of waveguide to various transmission line type transitions, waveguide and radial dividers and combiners, filters, microwave filters, suspended substrate filters, and microstrip filters. A lot of LMB front end circuits, polarizers, LMBs, waveguide transitions. So go ahead, please. You can visit the site, and I would urge you to subscribe because the subscription keeps me motivated that there is interest from people. I have about 4,000 subscribers now. I'd like to bring that up more. So, okay, so today, starting a new series, which I'm going to do, and the new series is basically is the direct RF sampled RF receivers. Now, as the name implies, this is basically what we call RF bits to RF signal to bits, basically directly without any frequency translations. And this is a concept that is of interest now. And it's starting to be feasible because a lot of the converters, ADD converters, have reached up to speeds up to 20 gigasamples per second commercially. And they're reasonably, they consume power reasonably. And so the trend right now in RF transceivers, transmitters and receivers for radars, for personal communications, for devices, communication devices, is to actually apply the receiver topology and the transmitter topology. That is RF 2 bits and then bits to RF, meaning digital to analog converter to the antenna. No frequency translation, just manipulation of the ADCs of the ADD or DAC. And on vice versa, for the receive side, it's RF 2 bits. Okay. So today I'm going to start on the new this new series with just part one, which is just an introductory. Okay, now this slide here is just showing you the channel, my YouTube channel, and here's the link if you'd like to subscribe to that. And my consultancy service is basically you can reach me with this number here. I have WhatsApp and Telegram if you like to call me from Europe and United States. Basically, this is what I do. I specify, I listed them here. So if you see a need for your organization, I'm very reasonably priced. I design stuff in weeks, and then the rates is in term of dollars per hour. It's as low as $10 per hour sometimes for some simple boards. So even for from a budgetary point of view, it's very, very attractive. So today's presentation, what I'm going to do is basically introduce the idea of picking up modulations data from the RF carrier on the antenna. Now, I'm not going to talk about the transmit side. I'm going to leave that to another series of lectures. But today's lecture, basically, I'm going to um, uh, work on the receive side only. That is antenna to ADD and then to demodulator or an FPGA platform. So we're going to talk about, first of all, introduce the RF receiver architecture evolution since from heterodyne all the way to nowadays, which is direct RF sampling. And then I'm going to introduce the idea of direct IF and RF sampling. As you know, in many cases, because the ADDs didn't have the broad frequency that it required, and it didn't have the speed that we can reach out to Ka band, Ku band, X band, S band. Before we used to translate the signal picked from the antenna after amplification and filtering, we would translate it to an intermediate frequency, that is IF here, and then we sample it, and then we go to DSP to extract data. But right now, what we're going to do is we're going to eliminate the IF stage, eliminate the down convergent whole section, which involves phase lock loop, synthesizers, IF amplification, IF filtering, mixers. So therefore, we're directly sampling from the antenna picked signal, which means we don't have the design approaches that we used to have once for RF receivers, where we would look at the mixer and the LO, MN, LO frequency, plus minus in the RF signal, and then work out on the picking the IF and seeing what all the spurs and harmonics where they become and so forth, and having to design a phase lock loop. All of this is gone basically with the idea of direct RF signal chain. Now, this is really, for right now, take it as it sounds from me, but later on we realized that we did eliminate the mixer and the frequency synthesizer. However, we're really having to add another frequency synthesis section, which is the for syncing the multiple ADDs and producing a microwave reference, signal reference to drive the ADD as a sampling frequency. All right, so we're going to talk about the ADC post-processing, which involves filtering, digital down conversion, and decimation filtering. Okay, and then the principle of direct RF sampling receiver. Of course, we're going to go deeper into this, and then we're going to go into RF ADCs and SERDES. And as you know, one of the complication that really got raised from direct RF sampling is really how are you going to handle all this gigabit of samples that are coming from the ADDs at a huge oversampled data rate, which involves sometimes up to 50 gigasamples per second. Each sample is depending on the ADD, whether it's 12 bits or 16 bits. So that's what created the concept of SERDES, which is serial interface that basically transports. It's a highway of data, billions of bits per second that are going to travel from the ADD onward to the FPGA or to the ASIC, which has the demodulation and so forth. So we're going to talk about this a little bit. Now, and then we're going to survey what's nowadays commercially available as in terms of ADDs. How far can we get? We're basically primarily talking about several companies that are dominating this market, namely Texas Instruments, that's one in the United States, Analog Devices, that's one in the United States, and then E2V, which is a UK company or partially UK US. These three companies, among them, they actually dominate the ADD commercial parts. Okay, and then I'm gonna end up with having to go into two examples that we're gonna use, basically the system view to demonstrate a direct RF sampled S-band receiver system design, and then direct RF sampled 28 gigahertz millimeter wave receiver system design. Now, these could be radar or they could be personal communications, SATCOM or whatever. All right, so just to give you a look ahead, this is basically what we do. This is the S-band direct signal sampling, and this is mimicking the antenna received signal and so forth, and then where we amplify the signal, and then we go into the intermediate match and filtering before the ADD. And as you can see here, there are no LOs, no mixing, nothing. We go directly from S-band to baseband, okay? And of course, in here, later on, in the coming sessions, we're going to start adding up the digital signal processing blocks that go in here, which really overcome the issues that come in from direct oversampling. Namely, when we direct sample, we end up with a digital IF signal in here, not a baseband signal, and then therefore, and it's way oversampled, way higher than the actual data rate. As you know, we all we need is two samples per symbol sometimes at most. So the data rates in here is way above the I mean the sample rate is way above the data rate. So we need to do decimation, filtering, numerical controlled oscillator mixing with a direct digital synthesizer the synthesis to bring the signal down to baseband. Okay. The other example is basically this is a 28 gigahertz signal source that mimicking a 28 gigahertz modulator carrier, which basically, as you can see, there's nothing in there except an ADD sampling. In this case, it's sampling at 12.8 gigahertz or gigasamples per second. Okay, and then we see the 28 gigahertz signal in here, and all we see is a low noise amplifier, a filter, another post amplifier, and then a matching section, and then the ADD. And of course, later on, we're gonna add more in this here to do some of the signal manipulations that has to be done in the digital domain. Okay, so we'll get to this, but let's first introduce some. I'm gonna go into full screen here and introduce more introduction to the concept. So the first thing is, I just want to remind you of this is the evolution trip of the radio frequency or microwave receiver topology. We started with super heterodyne that we can, even before this, there's more, but this is the ones that are based on digital signal processing. So first thing is the frequency is so high that we can sample it directly. So what we resort to is we start gradually down converting the signal to multi-stage intermediate frequencies until we reach an intermediate frequency which is acceptable to the ADD. And then, of course, we sample that signal at least twice the bandwidth rate frequency, and then we pass it onto the digital signal processing, which has the demodulator. Now, after this, Theo had realized, why don't we just go ahead and do direct conversion, meaning we get rid of the center carrier and we just bring in the modulations on the carrier, which is means the spaceband. And that's what we do here, which is zero IF or near zero IF receiver. That involves a direct conversion. So this LO frequency is exactly the same as the carrier frequency or near it for the case of near zero IF, and we low pass it, and then we digitalize it directly. Of course, now this one here really, even though it can cope with the moderate speed ADDs to high frequencies like 28 gigahertz millimeter band, X band, KU band, KA band. But there are multiple issues with this issue in here. Namely, the least that we look at a lot of times is, since this carrier is the same as this carrier, the sine wave modulated. So with each other, you produce a DC offset in here. The DC offset sometimes it eats up the ADD dynamic range, and you end up that's one issue, and then you got other issues as well for the imbalances. The imbalances in here, while this here doesn't have the issue of image rejection. There is no image to reject in here. But if these branches are not exactly equal with precision, we end up with an image frequency which we can't filter, and therefore there are a lot of issues with this. Another issue is the yellow in here is so strong compared to the signal coming in, so you may not have enough isolation in here, reverse isolation, so that this signal here, the yellow signal itself, will start radiating out of the antenna. And of course, the complexity also of trying to compensate for these impairments, you might call them. Now, with these two here, now these dominated really since the 50s, 60s, 70s, 80s, 90s, and the 2000s. And now we're in a new era where ADD is caught up. They're sampling at tens of gigasamples per second, and their bandwidth is sometimes could be on the order of 12 gigahertz. So having looked at that, then that became very attractive. Then that means we could actually capture the entire spectrum and digitize and channelize the desired signal inside the digital signal processing in here. So meaning you could have an ADD that is sampling, say, at 12 gigasamples per second. Now, when you do that, of course, that doesn't necessarily means you can only sample signals up to 6 gigahertz, which means it's the Nyquist bandwidth. That's not true. So the beauty of this is that we can actually subsample the RF signal, even though it's way more than the sampling frequency, which is what I'm going to introduce today to you. Okay. But what the important thing is that the bandwidth of this ADD can capture that signal, even though it's above the sample frequency. So we have two key parameters on the ADD that are sampling RF signal. First one is the bandwidth, and the second one is sampling frequency. Okay. All right, so this again shows pictorially the architectures. So we went from multi-stages heterodyne to a high IF what they call a single high IF. And then from this, we went down to zero IF or direct conversion. And then out of these three stages, we are now into this system in here, which doesn't involve any local oscillators, no mixing, nothing, no multi-stages, just a single shot, direct sampling the antenna signal after having passed through the low noise amplifier, some filtering and some post amplification and some anti-aliasing and drivers for the ADD. So therefore, uh, the concept really is simple as this. We have a DSP, an FPGA, or an ASIC, and then on both the receive side and the transmit side, what we're doing really is we're going from this ASIC with the data stream that we're trying to receive. I'm sorry, we're going here from the RF signal that is modulated directly to the digital domain, so it's RF 2 bits by eliminating the frequency conversion stage. And then likewise on the transmit side, we're really going from FPGA ASIC modulator to a DAC and then to the RF amplifier. We don't have any LOs or any frequency conversion, which means we're going from bits to RF. So RF to bits and bits to RF, both directions. That's the trend of the future. Okay, so let's look at the direct RF signal chain. Just as an example, this is a slide that I took from my own library of previous work. Let's say that essentially what we're doing in the old days, if you're trying to cover, for instance, the ISM band, which means it involves the 916 megahertz, the 900 ISM band, the 2400, the 5800, and the 3.6 gig, let's say, which is the 6G. Okay, all of these are basically Wi-Fi, remote control stuff, okay, personal communication stuff. So what we do usually is we have RF front ends for all of these separate antennas, and then we come down and combine them and amplify them. More the tunable filter in here, even though I didn't put an arrow through this. And then we convert them, all of these, depending on which one we want, we convert it to a common IF and then sample it. Okay, and we're done with this. And this people have done this for tens of years. And many of the devices that you use nowadays is actually based on this architecture. However, if we can do this, if the ADD in here caught up in bandwidth and frequency, sample frequency, what we could do is commonize. We would have these come all the way and through a broadband amplification and then filtering, and then we can capture the whole spectrum. This spectrum is nothing from say DC to 6 gigahertz. Nowadays, most ADDs that are sampling used for RF communications can do this, can sample that do have the bandwidth to actually capture the entire bandwidth. And of course, when we capture it all, we amplify it all in one, and then we just filter the whole band, the entire block of band, and go into the ADD. And of course, somebody might come in and say, well, how are you going to deal with all these dynamic range signals? Because a lot of these sometimes you can find 30 dB power variations between these various signals on an antenna. Well, that's the ADD has to cope with that. And that's what I'm going to be illustrating in the next coming videos. Today, we're just going to introduce the concept, but how do you actually do this? And I will hint to that direction in a moment. So now let's say that we're doing more than multi-channel system, same thing, the same signal. We pick it up and then we go through ADDs and then we can channelize all of this in the digital domain. So your digital domain, depending on which service or simultaneously sometimes, you can actually demodulate any of these signals simultaneously. So in fact, there are some people that build RF systems for like critical mission systems where they can have the same data coming on different carriers to mitigate interference or fading problems. So if that's so, you can actually detect this same data on multi carriers and combine the data stream or do some kind of diversity combining or compare errors and there's a lot of ways to get reliably the data still come in despite the fact there is interference or something else. One of the ways, if you look at the this here from analog devices, I took this slide. So basically, when you're dealing with a system like this, where we have a, say 6 gigahertz bandwidth, you're capturing simultaneously. You end up with looking at this, and you see a whole variety of signal levels. So each one of these frequencies, modular carriers, each one of these services, they come in depending on the distance from the receiver or the telco services. Some services, cellular, might be transmitting 50 watts from a base station, where some Wi-Fi device in your kitchen may be transmitting 100 milliwatts. So there's a tremendous dynamic range that we have to deal with. In addition to this, we're really dealing with sometimes CW interferences and interferences that are undesired at high power level. So if when you have this, if you want to go directly antenna to demodulation, you really have sometimes what you could do is you could have a separate front end, separate multiplexers, separate filtering, separate antennas, and then you can individually, okay, vary the gains and the bandwidth of these filtering here for every individual one of these, and then you combine them and you go to a common ADD. And once you do that, of course, now you've actually compressed the dynamic range so that you can accommodate capturing all of these without, for instance, saturating the ADD. Let's say if you're trying to receive this signal in here, this interference in here, this CW interference here, this will saturate the ADD and you will not have that much dynamic range left to see the modulations on these other services, unless, of course, you resort to separate amplification, automatic gain control, and automatic tuning for these paths. And there are lots of products nowadays that are doing this. Okay, so the benefit of doing direct RF signal sampling from the antenna is really the elimination of the conversion frequency translation stage, which involves getting rid of the mixer, getting rid of the local oscillator, and usually these guys in here, they eat up power, they eat up size, the cost. So when you get rid of this, you go directly. So now you have a lot of flexibility because you're capturing actually the entire band, and inside the digital domain is where you can selectively pick and choose the services that you want, and then you can vary the bandwidth, data rate, whatever. Okay, so this is the beauty of RF direct sampling versus IF sampling like we do conventionally. So again, it's just basically we're going from here to here by chopping this part for right now. But later on in the coming sessions, we're going to end up saying, well, wait a minute, we took the LO out truly, but now we have to have an LO moved to the A to D because we have to provide an accurate sampling frequency reference, which involves really building a synthesizer as complex and even more complex than the one used in the down conversion. In addition to that, we have sysref reference signal for the DSP for trying to precisely time the multiple ADDs in the digital signal domain, which means that really we moved we removed the conversion frequency conversion stage, but we really moved the complexity down to the ADD. Similarly, when you remove the mixer, when you remove the mixer from this, you don't have any more frequency planning for the receive frequency versus the selection of the IF and the interferences, because in there, what we used to do, if you recall, um, is trying to accommodate search through the MNLO, the the harmonics of the LO and the harmonics of this signal here with the interferences. All this interaction has to be analyzed in spreadsheets and like what IF in the system will, to try to see, make sure that the IF selected is free of spurious and harmonics. We did eliminate that when we go through mixer. That's right. But okay, now really the complexity went down to the A to D converter. The analog digital converter now, we have to do frequency planning for it, because what happens is the analog digital conversion process with the harmonics of the desired signal, with the aliases, with the sampling frequency, with the mismatches between the ADDs, the interleaved ADDs, which we have to resort to using to speed up the sample rate. Now, this created another issue, which is the system frequency planning for the ADD converter, and that's we're going to have a session basically in the coming videos on this. Okay, so let's go further down the DSP chain and just look at what we do. So we have this chain in here, and this is from, I think, from analog devices. Yes, it is from analog devices. You can see the Hittite parts in here. So we receive a signal and we sample directly, let's say in this case at 4 gigasamples per second. And we do filter it first, and then we have to create the complex domain signal, which means the I plus the Q, JQ. Okay, and we do that by a numerical controlled oscillator in the DSP. This could be done in the FPGA. It used to be done in the FPGA nowadays, but a lot of the ADDs now are starting to integrate that into the ADD. So, like in this case, for this device here in the year 2025. Now, the reason I'm insisting on saying the year, because let's say somebody was watching this video in, say, 5 years from now, this will be primitive. So we really have to mention the year. Otherwise, because this evolves so fast that in 10 years, this will look like, something else. So anyway, what we do is create the INQ in here, and the way we do this is we take the signal and multiply it by a cosine and sine, just like we do in the analog, and then low pass it first to get rid of images and aliases, and then we decimate this, because usually this signal here is running at such a high rate that we really don't need all of that sampling. We need to reduce the sampling so that we can slow down the DSP in here to preserve power and accuracy. So, like in this case, if there are decimators that you can program or bypass them, and usually the decimation is usually 2, 4, 8, 16, 32, depending on the width of the bandwidth that you want. So, what this stage is doing is basically taking the sample signal here, multiplied by either j omega t in the analog domain, which is really just provide T with NTS basically, and that is what this is. Okay, so the decimation now is critical in this case, because what happens actually, decimation here it narrows the bandwidth and it slows down the sample rate, and also provides an improvement in signal to noise ratio, because the noise bandwidth is not the same. So whatever signal to noise ratio we're dealing with in the ADD in here is going to get improved by the ratio of the Nyquist bandwidth that are for the ADD divided by the number of the number used for decimation. Okay, and when you do that, of course, you really have to be careful, because when you decimate, and I don't want to make this into a digital signal processing class, but if you are aware of the sample frequency, when you sample a signal at such say fs rate, basically you have fs over 2, which is the Nyquist bandwidth. So you do get the desired signal, plus you get multiples of this at every f sample. So like in this case, it's 0 fs. So there's one here, there's an image at the negative frequency in here, but this also repeats all over. And now, usually, what we do, we have a low pass filter, so we low pass it so that we reject these guys in here. But if you decimate, okay, if you decimate, what happens is you actually bring these images, these multiples of the same signal around the sampling frequency. And of course, this one is inverted to this one, the spectral inversion. Okay, what happens is you bring these narrower and closer and closer depending on the ratio you're sampling. Okay, so like in this case, for instance, if you're sampling by 2, um, what you at fs over 2, you're going to get this replica translated down to here. You're going to get this and this, and therefore get very close to the signal that you're trying to basically process. And that's when you have to really use a low pass filter. So whenever you see a decimation, you're always going to see a low pass filter, okay? Even though it's not shown in here. And of course, the signal to noise ratio in this signal here, which is decimated, is going to be proved by the 10 log of the decimation rate that you're doing. We'll get to that. Yeah. Okay. Well, here it is actually. So the signal to noise ratio in here of the signal past the after the ADD, and we will derive this equation again. So for right now, just take it as is, which is the absolute value of the noise spectral density of the ADD, which is really given in the data sheets. That depends on the number of bits and some other issues. Minus the 10 log of the Nyquist bandwidth, which is the sample rate divided by 2. That's really here is basically your signal to noise ratio. And all that does is that you're saying that the signal to noise ratio after the ADD is basically the noise spectral density, which is per hertz, dBm per hertz, for the ADD. Above that, by this much in here, okay, which is fs over 2. But if you sample it, that this one here is going to be reduced, and that's basically what we have to do. All we have to do is just basically divide this by the decimation rate. As you can see now, now pictorially, what really is taking place in here, because when you look at this here, this signal is not at baseband. We really want this signal here. It's centered at 0 hertz, okay, in the baseband to extract the modulations. But that's why when this signal comes in here, because when you subsample, the alias that is resulting from subsampling of a carrier, an incoming signal with a sample rate that is above the frequency itself, you're going to have an alias. And that alias, so really a lot of times you can plan as much as you can, but you will not be at baseband. So what happens is you still need to rotate it to baseband, move it in frequency, and that's shown in the picture in here. So what happens is this is a signal that sits out there somewhere at some Nyquist zone, and when we subsample it with the ADD, we're going to result in an alias which is very close to the baseband. Now, a lot of times this we don't even care sometimes if it's flipped around, if it's spectrally inverted, is because we can do that in the DSP domain. All that is just changing a sign or interchanging I and Q, the quadrature signal. And that results in the putting the frequency back in the right orientation. So once you get to here, now we need to translate to here, and that's where we multiply it basically by a CW, which is a local oscillating digital domain, and bring it to baseband in here, okay? And of course, in that case, right after that, you do decimation, and that decimation is going to prove the signal to noise ratio. Okay, so direct RF sampling receivers. So this really summarizes some of the things that we're gonna that we just talk about. So, and that is basically Let's see now. So the RF sampling receiver directly captures signals at RF frequencies and uses a numerical controlled oscillator to shift the signal to the baseband or to desired digital IF frequency. In some cases, you might end up with somebody in the digital domain, his DSP, he wants to operate not at 0 hertz, somewhere else, for instance, with a frequency rotation. In either case, this is really what's happening. Subsample, grain areas rotated to this or not rotated at all. That's what this is saying. The translation from RF carrier to baseband is carried digitally using a numerical controlled oscillator with a digital down converter. This is called digital down converter, this piece here, really, because you're down converting from some alias location to baseband. So there is a flexibility, bandwidth, and channel selection, of course, and that's because really this signal here, once we decimate it, we can vary this decimator, this filter, and in that fact, you can have multiples of these in parallel to the capture signal. So you can have multiple ECOs and in the digital domain, and you get in parallel, you're actually receiving different signals at different offsets from each other. And you move them all to baseband, and you can do processing all simultaneously. So direct RF sampling receiver eliminates the RF mixer. That's right. We did eliminate the RF mixer, just like we did in here. And then, of course, RF synthesizer is eliminating, and then the IF channel filter. All of that, of course, saying that we eliminated these and eliminated an IF processing. Okay. With direct RF sampling system, there are no N by N spurs because there is no mixer. That's right. There is no frequency planning of LO and mixer spurs and harmonics, but just like I said, the ADD input frequency harmonics, aliases, and sample frequency spurs still needs to be planning. In addition to the interleaved frequency interleaver ratio, which is 4 or 2 nowadays in the commercial available parts, and then the mismatch in between timing and amplitude between the interleaved ADDs. All of these we're going to talk about. Okay, so let's see. Let me just